Hello and welcome to another CS Tutor Center video. In this video we're going to talk about the problem finding all anagrams in a string. But before we get started, please go ahead and subscribe to the channel if you're enjoying these videos. When you subscribe to the channel, that lets me know that you enjoy these videos, and as a result I'll make more of them. Alright, let's get started. So this problem says, given two strings S and P, return an array of all the start indices of P's anagrams in S. You may return the answer in any order. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So in this example below, they have this string A, B, C, and then the anagrams they find is one right here, and this is the start index, which is 0, and then they also find one over here, and the start index here is 6, so 0, 6. Okay, and then the AB here, so we got one at 0, starting at 0, we got one starting at 1, we got one starting at 2. Whenever looking at these problems, you always want to start thinking what kind of coding pattern you'll use. And in this one, a sliding window would work really well, because what we could do is we can make a window be the size of this string, and what we'll do is we'll start that window size out over here, and then we'll see if those letters are inside of this the letter counts inside this window match what we need from here, from this string. And if so, then we'll record that start window index into the array. And then we'll just slide over one to the right. And as we slide to the right, one letter leaves the window and one letter enters the window. And we keep on doing that sliding, and what happens is that we only have to go over this once as a result of that. And if you give me some string like this, which has n characters, and I only have to go over that string once, I've gone over all n only once. That's linear. So that means the big O is linear. And then we want to think to ourselves, is there a way that we can have a big O that would be faster than linear? And the answer is no, because if we think about this problem, let's think about this string like this. We have some type of string, but I'm going to put a bunch of question marks in here because we have not yet revealed the letters inside that string. And if I can do better than linear, that means I wouldn't have to reveal one of these question marks. But I know I have to reveal all the question marks, because maybe one of them is, the one that would be the key that would let me know if the letters are inside of this string. So let's go like that. So I know I have to reveal all the question marks. I know that means that I have to look at all the letters at least once. So I know I can't do any better than linear. I know that the sliding window can solve this problem in linear time complexity, so the sliding window is the way to go. All right, so we'll go down to the constraints to see what else we can learn. The constraint says that the S string and the P string are between size 1 and 3 times 10 to the 4 inclusive. So that's what that means, is that the P string, which has our pattern of what we want to see is inside of the S string, this P string can be larger than the S string according to these constraints. And if the P string is larger than the S string, then we could just return false, because we wouldn't be able to find an anagram of P inside of S if P is larger than S. Okay. This constraint here tells us that P and S consists of lowercase English letters. So then we know that the number the maximum number of letters that we would be working with is 26 because the English alphabet has 26 letters. So we can use an array of size 26 to keep track of the frequency count of each of these letters that is inside of P. Okay, and that will be better than using a hash map. We could use a hash map. In fact, if this constraint wasn't here, and if there was no bound on what these letters could be, if we could have all kinds of weird punctuation and all kinds of Unicode characters, then we would use a hash map in that case, because we wouldn't know how big our array needs to be. We wouldn't want to have some massive array. So we would use a hash map in that case. But in this case, it's only 26. And so we can use an array. And the reason why it's better to use an array is because the real world runtime is going to be a little bit faster. So you know that both the hash map and also the array has a big O time complexity of constant. So it's not going to change the big O time complexity. But the real world runtime is going to be faster because when we access a value inside of an array, we give it the index and it's a direct lookup. There's no delay there. But when we access a value inside of a hash map, what happens is there's a hash function that calculates the hash code, which mods that unique number from the hash code with the size of the array that's inside of the hash map to keep it within the bounds of that internal array. And then it's going to go to that array location in the hash map, which each array location in the hash map is a linked list, and it will then add on to that linked list the value. And the reason why each location inside of the array of the hash map is a linked list is in case there is any collisions. And so really, the hash map, you could run into a situation where there's a lot of collisions and that collision slows it down. But averaged out, it's still constant. So the real way to think about the time complexity on the hash map is that it's going to be the time it takes to iterate over the longest linked list in that array where all those collisions, where the most amount of collisions occurred. Okay, so I have another video where I draw it out. I'll put that in the description here, so you can click on that to look at me drawing out the hash map and explaining that. This video is also part of a sliding window playlist, so I'll put the link to that playlist in the description too. So this is example 1 of the problem. In this example, we have P, which is the string that we're trying to find all the anagrams for inside of this array. We have a variable called matched. I'll explain what that means. We have a variable called unique letters, which is going to keep track of how many unique letters we have inside this string. I'll set that to 0 and we'll build that up. Then we have this array over here that keeps track of the counts of these letters. And then I wrote this over here, which if you go look up a ASCII map, that's what this is. I'm just going to do the first 3 here. So we have the decimal value of the character A, which is 65, the decimal value of the character B, which is 66, and the decimal value of the character C, which is 67. We'll use this, the ability to know this, we'll use that to create the count of these letters. So let's get started with this. So first we're going to set up this counts. So we read A from the P string and we say we're going to do A, we just read A, and then we're going to subtract off A from it, which equals 0. So we're doing this math to figure out our index. So we read A, we subtract off A, we get 0, so we go to 0 and we're going to increment this to 1. and then we read B, and we subtract A off from B, and that's index 1, so we go to index 1. And then we read C, and we say C minus A, which is index 2, so we go to index 2. Okay, so now we have our counts. Okay. And then let me back up a second here. Let me go back real quick. When we're doing this, there's also one thing we're going to do. What we're going to do is when we, let's start over and I'll explain that. When we read A and we say A minus 0, we go to index 0, we see that it is 0. Since it is 0, that means we just encountered a letter we hadn't ever seen before, so we're going to increase our uniques. This keeps track of the unique letters we have. Okay, and then this gets increased to 1. And then we read B and say B minus A is index 1. Oh, there's a 0 there, so that means we haven't ever seen the letter B before. So let's say we have another unique letter that we haven't seen. And we'll increase this over here to say the number of B's we have. Then we read C, and we say C minus A, which is 2. So we go here, and we see, oh, we have another 0, so we've never seen C before. So we're going to increase our unique letters to 3 now. And this also increases to 1 to say that we have 1 C. Okay, so we have 1A, 1 B, and 1 C inside of this. And this string consists of 3 unique letters. Now we shall work on our sliding window. So we start out at location 0, 0. We see there's a C that's inside of our window. So we say C minus A, which is 2. We go to location 2, and we see there's a 1 there. So there's a 1 there, and we decrement to say that we have to account for the C that's inside the window. So we decrement. Now, since that became 0, we know we just fulfilled all the letters of some unique letter inside the window. So what we did is we just fulfilled all the C's that we need. So all the C's we need is in this window. There's only one of them. So all the C's that are inside this string are in this window, so that's good. So since when we decremented this number, it became a 0, then we say we increase this matched to 1. The matched represents that we matched all the letters of some kind of letter we're interested in. So in our case, we matched all the C's. So the match goes to 1. Because what we're going to do is when the matched ends up equaling the unique letters, that means that we've matched everything inside of this string. Okay, so now we are going to increase this window, and the B entered the window, so we say B minus A, which is 1, so we go to here, and we decrement. And that just became a 0, so we come to the matched and increase this to 2. Okay. And before we loop, at the end of our for loop, we're always going to check to see if the window end, which is 1 right now, if that is greater than or equal to the last index of this string. The last index of this string is 2, so it's not. Okay, and I'll explain why we do that when we run into this scenario where it is greater than or equal to it, which is on the next go around. Okay, so now in our for loop, we're always increasing the window by 1. So we increase the window by 1. A entered the window, so we go to location A here, decrement. That became a 0, so we increase the matched. And now the matched equals the unique letters, so we have fulfilled all the letters that are inside of this. So we found an anagram. So what we're going to do in indexes is we're going to keep track of the window start. So the window start is at location 0, so we add that in there. And then now the window end, which is 2, is greater than or equal to the last index of this. So the last index of this is 2, and the last index of that is 2. When that happens, we know we need to shrink our window. So shrink when we have window end greater than or equal to p dot length minus 1. Okay. So we shrink this window. So C just left the window. So we go to C, which is going to be C minus A, which is 2. We see that it was a 0, and we're about to increment it. So it was a 0, so we need to go to this matched and decrement the matched because that's leaving the window, and we're no longer going to have all the C's inside our window. So we decrement that, we increase this to 1, and then now when we loop, then we increase our window size. So E entered the window, but that's not part of anything. And this window end, which is 3, is greater than or equal to 2. So shrink that. B just left the window. So we go to the B, which is location 1. That is a 0, so we decrement our matched. And we increment this. And we grow the window. B just entered the window, so we go to B and we decrement. That became a 0, so now we're going to increment our matched. And our window end is greater than or equal to p dot length minus 1, so we're going to shrink this window. A just left the window, so we go to A. It was a 0, so we're going to decrement this matched. And so we increment this to 1. And then we grow the window. A just entered the window, so we go to A, which is 1. So we decrement. That just became a 0, so we increment our matched. And window end is greater. This is true, so we shrink this. Okay, and then we increase this. B just entered the window, so we go to B, which is location 1. It was a 0, and we're decrementing it, so it's a -1. We got more than we need in there. This is true, so we shrink it. B just left the window, so we go here, we increment. And then we grow. A just entered the window, so we go to A and we decrement. And then we shrink this window. A just left the window, so we increment. And then we grow. C just entered the window, so we go to C and we decrement. That just became a 0, so then we increment our matched, which is 3. Now matched equals unique letters, so we append the start window start to this array, which is 6. And then this is true, so we shrink this. B just left the window, so we go to B, decrement. D entered the window. Okay, and then we're done. And this is the answer, 0, 6. Okay, so let's go code this up. So we need to have a list of indexes. This is going to keep track of our answer. This is what we return. Okay, and then the other thing we needed was keep track of the frequency counts, which is the English alphabet. And then we also wanted like the unique letters. Okay, and then we're gonna go ahead and populate the frequency count and also update the unique letters. So go like this, and this is coming from the P string. Okay, so we're gonna create this index. So C minus A, and then we're gonna say if the frequency counts of the index equals 0, then we've never seen this before. And we'll increment the unique letters. Okay. And then we increment the count of that letter in the array. Then we're going to make a matched variable. And then we'll do our sliding window. Ah! And we're going over the S string. Okay, and then we're going to get our end index. And subtract off the A to convert it to the index. And then we will decrement from the frequency counts the end index. And then if that became 0, then we increment our matched, and if our matched ends up equaling the unique letters, then we have found an answer, and we put our window start in here. Okay, and then if our window end is greater than or equal to the p dot length -1, then we know we need to shrink the window. So we'll calculate our start index, which is going to be s dot char at window start -a. And we'll check to see if that is currently 0. So if it's currently 0, then we know we need to reduce our matched because we're about to, because that letter's leaving the window. So we got to account for that, and we account for that by increasing the number of letters that we got to find again in the window. Okay, so that shrunk it, that we got the start index, we checked to see if it was 0. If it was, we do their matched, and we incremented that. That looks good. Let's run that. Okay, good. Okay, great. So we have the answer there. And then I also wrote this in Python here. Oh yeah, one more thing. Let's go back over here. You know what I could have did? It was I could have said that scenario we talked about where the p dot length, if that's greater than the s dot length, then we'll just return false. So before I run that, check it out. We're at 68. We beat 68, and then after I add that in there, we'll be faster. We have a compile error. So super fast because it crashed and didn't work. All right, so it ends up being a little bit faster. Instead of 68, we have 74.93. All right, so then we'll go to the Python code. All right, so same thing here. So we did that, and it's just all the same code, just in the Python syntax. The only thing is to know is that in Python you have to use the ORD function to convert from the character to the decimal value. This is initializing 26, a list size 26, all populated with zeros. I'll give you some time to look at this code. I'm going to scroll down now. You can pause the video if you want to look at it longer. Okay, so there we have it. All right, so if you are enjoying these videos, please subscribe if you have not had a chance to. Please subscribe because that lets me know that you want me to make more of these videos, and when I see that subscription count go up, then I say I will make more of these videos. Also, if you like this video, go ahead and like it, because then that will mean more people will see it in their search in YouTube, and then more people will subscribe, and then I just get more motivated to make more videos. All right, well, thanks. Have a good rest of your day.